Okay, so we're going to look at horizontal and vertical asymptotes today, plus the squeeze theorem. So you need to pay good attention today because there's a lot of things here that in years past I just haven't done as good of job with. So I want to make sure I do a really good job of making sure you understand the distinctions between a horizontal asymptote and a vertical. And yesterday I think I mentioned, and I'm going to have you write something down here just in a second. So you're going to make a mental note here and physically write it down on your paper or in Notability here. Horizontal asymptotes, as we talk about those, and we kind of got, this is where we didn't get through all this yesterday. Horizontal asymptotes, the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x equals b or the limit as x approaches negative infinity of f of x equals b. And before I get through and explain this definition, I think most of you know what a horizontal asymptote is. It's the graph approaching a horizontal line, but specifically this definition kind of points out where it approaches the horizontal line. Because what classifies a horizontal asymptote is not that it just approaches a line, but it approaches a line, a horizontal line where? At what? At the end-tails, okay? At the limit as x approaches infinity and the limit as x approaches in negative infinity. So at your end behavior. So at your right end behavior and your left end behavior. Now, the comment I want to make about a horizontal asymptote does not represent an undefined value. A vertical asymptote does, but a horizontal asymptote does not. A horizontal asymptote is simply what the graph is tending towards at the ends. It's what the graph tends towards at the ends. Okay? It is not an undefined value, which means, and I want you to write this down, a horizontal asymptote, the graph of a function can cross a horizontal asymptote. You can cross a horizontal asymptote. In fact, you can cross it an infinite number of times. What makes it a horizontal asymptote is after you cross it an infinite number of times, at one of the tails you have to approach that horizontal line. So you might have a graph, let me just make a point here, is it might look like this. Then it eventually approaches something. And as long as it approaches something at either end, it doesn't have to be both, either end of the graph, it makes it a horizontal asymptote. Okay? So you can cross a horizontal asymptote because it's not an undefined value, it's just what the graph approaches at the ends. Alright, so we're going to look at three situations that you have with horizontal asymptotes. There's three situations, okay? The first situation is that you have no horizontal asymptote. Can anybody think of a graph that has no horizontal asymptote? Parabola, perfect. Okay, no HA, write that down, no HA. First example would be a parabola. You could think of others. I mean, a disco curve would be okay too. I'm going to do a disco curve just because I want to be different. Okay, celebrating diversity. Okay, you can have a disco curve, you can have a parabola, you can have a line. Any polynomial function really is going to have no horizontal asymptote to it. An absolute value function has no horizontal asymptote. We could think of others. A bird has no horizontal asymptote to it. So those are examples of functions that have no horizontal asymptotes. What's another situation that you can have? Well, yeah.
Can you ever have more than one?
Well, let's start with one. Can you have one? Is it possible for a graph just to have one asymptote? Give me some examples of graphs that have just one asymptote, one HA.
Cosine and sine graphs?
No, they just oscillate forever. Huh? The boomerangs, okay, there's one. Some people would say, no, that's two horizontal asymptotes because it's approaching at the right tail and left tail. No, that doesn't matter. I'm talking about two different. Okay, so here's the boomerang. Oops, I screwed up. I gotta erase that. So one HA would be the boomerangs. Let's try again. Okay, your reciprocal function, 1 over x. Okay, it approaches 0 at both ends. So the horizontal asymptote there would actually be y equals 0. Okay, that's what the horizontal asymptote is, y equals 0. What's another example? Volcano. I'm not going to draw that one, but the volcano would be another example. Can you think of one particular graph that has one horizontal asymptote, but it only approaches it at one end? J-curve. Okay, your exponential curve, e to the x. That's an example of a graph that has one HA, one horizontal asymptote. Remember, the e to the x crosses at 0, 1, goes up to the right, and it approaches 0 to the left. So that horizontal asymptote is also y equals 0. Okay, you see that? That horizontal asymptote is also y equals 0, but it only approaches it at the left end, which is why this word here is so important. Because it only has to approach at one end for it to have a horizontal asymptote. Alright, now we've got no horizontal asymptotes. We have one horizontal asymptote. There is such thing of a graph having two horizontal asymptotes. 2HA. I've got one for you. You're going to love it. Here we go. Y equals inverse tangent x.
What about the circle one?
It's not a function. Okay, y equals inverse tangent x. Here's an example of one that has two horizontal asymptotes to it. I don't know if you remember doing this, but before Christmas we did the inverse trig functions, and we graphed tangent, and then we graphed its inverse. We graphed sine, then we graphed its inverse. We graphed cosine, we graphed its inverse. And we did that so that we could get the restrictions for the inverse trig functions. If you remember, inverse sine was restricted from negative pi over 2 to pi over 2. Remember, your calculator only tells you answers between negative pi over 2 to pi over 2. How many recall that? Inverse cosine from 0 to pi, at least I know it. Okay, inverse cosine from 0 to pi. What about inverse tangent? It's also negative pi over 2 to pi over 2, but not including the negative pi over 2 and pi over 2. And that's because it had VAs. Now, what we did when we proved that is we actually started with the sine graph, and then we switched x and y, and we reflected it over the line y equals x, and the sine graph got tilted. It rotated 90 degrees to the right. We did the same thing with the cosine graph. Did the same thing with the tangent graph. And when you do the tangent graph, it's really interesting, because the VAs become what? HAs. And what happens, you get an HA.
Oh yeah, that has like
Vertical asymptotes it does. But we had to restrict it for it to be a function. So we restricted it between two asymptotes. And it looked like this. Kind of looked like a lying down disco curve, but a lying down disco curve goes up forever. Where this approaches an asymptote. And that was the inverse tangent. And this had two horizontal asymptotes. It had a horizontal asymptote at pi over 2 and negative pi over 2, so we could say it's plus or minus pi over 2.
yeah, but isn't like the domain range like
The domain is all real numbers. The range,
it's infinity at that?
no, the range is from negative pi over 2 to pi over 2. Okay, the highest this graph will go is pi over 2, the lowest it'll go is negative pi over 2. Now, when you looked at the regular tangent graph, its domain was not all real numbers because it was whatever the x couldn't equal whatever the asymptotes are. The range was all real numbers. And when you flip it, though, you would essentially have multiple sets of horizontal asymptotes. But if you do that, will it be a function? What's the reason you can't have more than two horizontal asymptotes? If you do the vertical line test, it's not going to pass the vertical line test anymore. Okay, so you can only have the greatest amount of horizontal asymptotes you can ever have is 2. You can't have more than 2 horizontal asymptotes. That's it. Cut off right there. 2 horizontal asymptotes, done. All right, and that right here, inverse tangent, lying down. It's not a true lying down disco curve because let me explain something. X to the 1/3 goes up forever. It goes down forever. It doesn't approach a value. Same thing for the square root function. Okay, so don't confuse those. Those don't have horizontal asymptotes, but this does. Okay, and so those are our horizontal asymptotes for this. Now, if you were looking back at regular tangent, those are vertical asymptotes, and there are an infinite number of vertical asymptotes. You can have more than 2 vertical asymptotes. That's fine. All right. So those are the 3 situations we have with horizontal asymptotes. What I want to do is kind of clarify some steps that you can take to find horizontal asymptotes, and there's really only 2 steps. So if you go down here and you can write down what those 2 steps are. So let me scroll up just a little bit. To find horizontal asymptotes, first you're going to find the limits. Find the limits as x approaches positive infinity and x approaches negative infinity. So find both of them. Now here's the cool thing. Anytime we do limits as x is approaching positive and negative infinity, we can use our shortcuts. Okay, we're going to be able to use some shortcuts with positive and negative infinity. That's really nice. And here's the other thing we know is that most of the time, is it really going to matter if we're approaching positive or negative infinity with our shortcuts? Now, what's the only time it really matters when you're approaching positive, negative infinity? Huh? No, you guys.
0.
Oh, no.
When there's roots.
Yeah, when there's roots. It was like the problems we did yesterday where you have piecewise. And then it mattered which tail you were going to. Okay, because one tail might be approaching something different and the other tail might be approaching something completely different. And we'll look at the examples and you'll see why. So most of the time it's not going to matter that you're approaching positive or negative infinity. You can just do one of them because the other end's going to be the exact same thing. Kind of like the boomerangs, both ends go to 0. Volcanoes, both ends go to 0. But sometimes there are some problems like the inverse tangent where one end goes to one thing and the other end goes to the other something else, and you've got to do both to figure out what both of them are. All right. Once you find those limits, okay, once you find the limits, the limit values, and we'll call that L, the limit values, and we'll call those L, are the HAs. So, write horizontal line equations. And you can just do horizontal line equations would be y equals L. So whenever we find that limit value L, whatever it is, and it is a constant, we could call it C, but I'm just calling it L for the limit value. So whatever that limit value is, those are the horizontal asymptotes. So write horizontal line equations, y equals L. So make sure you finish it and say, okay, these are the horizontal asymptotes, y equals 2, or y equals -3, or y equals 0, or y equals pi over 2, or whatever it is. Okay? Any questions? All right, good. Let me do some examples with you now. Scroll down and to the next page, and I've got some examples that you can look at. It says using any technique, that means algebra, orthograph, and calculator. Now I'm going to tell you, these three that I have here, I'm going to pick a couple in your book that we can use the calculator with. These three examples, I do not think you need your calculator for. I think you can do these all with shortcuts. So let's take a look at them. The first one, f of x equals x minus 2 over x to the 4th minus 3x plus 1. If I look at that, how can I do that using a shortcut? Huh? Yeah, you can do it with your power rules. Okay? So if I do this problem, I'm going to look at it. I'm going to look at both limits. Do I need to do both ends? Let me ask you this. If I'm going to do the limit as x approaches infinity, am I really going to need to do the limit as x approaches negative infinity? No, because the shortcuts, the rules really didn't matter if you're approaching positive or negative infinity, did it? Only when it's piecewise. Okay? Only when it's piecewise is it going to matter. So if it's not a piecewise function, you don't really need to approach both positive or negative infinity. That'd just be, you're just going to get the same answer twice. Okay? So x minus 2 over, what's that? Let's do this. What's the highest power on top? X, what's the highest power on bottom? X to the 4th. So is the power bigger on top or bottom? Bottom, so what's the limit value? So what is the HA?
0.
Y equals 0. And we'd get the same thing at the other tail, because it's not going to matter this time since we're approaching negative infinity. Do the other two real quick on your own. See if you can get those.